In this video, I'm going to demonstrate how to conduct a Cochrans queue in SPSS. And just briefly, and as I mentioned in the textbook, a Cochrans queue is useful to test the hypothesis that the percentages are equal across two or more levels in a within subjects factor. So it's a repeated measures type of analysis, similar to the one-way ANOVA, except that instead of continuously scored data, it's useful for dichotomously scored data, hence the percentages. So in this example, the students rated whether they were taking the unit simply because they had to versus because they wanted to, and a 0 corresponds to responding to the question because I want to, that is because I want to study statistics, and 1 represents I'm simply studying statistics because I have to. And recall that the teacher hypothesized that the percentage of students who are taking statistics simply because they have to, that percentage will change across time, and the teacher's hoping that the percentage will reduce in a statistically significant way. That is, that fewer and fewer students will be taking it because they have to. Now, one thing I'll note about doing Cochrans queue is that you don't get very useful descriptive statistics, so you're best to get the descriptive statistics separately through the descriptive statistics utility. So go into Analyze Descriptive Statistics Frequencies, and then place the 3 levels of the within subjects factor into the variables box, and make sure that Display Frequency Tables is selected, and you'll get the percentages across the 3 levels. So click OK. And here we can see that the sample size is 52, and that at the semester start, the percentage of students who said that they are taking the statistics unit because they wanted to was equal to only 15.4%. Let me just stretch that out. Because I want to, 15.4%, and because I have to, 84.6% of the students said that they were taking the stats unit simply because they had to. However, by mid-semester, the percentage of students who were taking the unit because they wanted to increased to 25%, and then by the end of the semester, the percentage who were taking the stats unit because they wanted to increased to 36.5%. So it started off at 15.4 and increased to 36.5. And the Cochrans queue statistic will test the null hypothesis that the percentages are equal across the within subjects factor, which in this case is period of the semester. Start, middle, and end. So in order to carry out the analysis, go into Analyze, Non-Parametric Tests, Legacy Dialogues, and K-Related Samples. And then place the 3 levels of the within subjects factor in the test variables box and click Cochrans queue and deselect Friedman. Click OK. Here are the basic frequencies, increasing the percentage who said 0, which is because I want to, has increased in frequencies 8, 13, 19. That was reported here as well, 8, 13, 19, but ultimately you want it expressed as percentages because it's more readily interpretable. Now to the null hypothesis that the percentages 15.4, 25, and 36.5 are equal, the null hypothesis has been rejected. Cochrans queue equal to 16.545, and with 2 degrees of freedom is p less than 0.05. In fact, it's p less than 0.001. Now, just like a one-way within subjects ANOVA, just because you get a significant f value doesn't mean you really know where the significant differences lie. At the very least, we know that the difference between the smallest and the largest percentages is going to be statistically significant, but we don't know if the difference between start of the semester to the mid-semester is statistically significant. So to the question, are students rating that they want to take the unit, is it increasing by mid-semester, or does it take the whole semester for a statistically significant effect to be observed? In order to address that question, we have to do multiple comparisons or post hoc tests. And in this case, we can just do a series of Cochrans queue, testing the difference between start and mid-semester, start and end semester, and mid and end semester. So let's do that. Analyze, Non-Parametrics, Legacy Dialogues, K-Related Samples, and let's just look at semester start and semester mid. Is that statistically significant? It is in fact. 0.025, p less than 0.05, with a Cochrans queue of 5.0 and 1 degree of freedom. So the difference between 15.4% and 25% is statistically significant. And so the researcher or the teacher could assert that even by mid-semester, a statistically significant increase in the percentage of students who want to take the unit is observed. Now let's do the next one. Analyze, non-parametrics, legacy dialogues, k-related samples. Let's go start semester, end semester. We know that one's going to be significant because at the very least the biggest percentage difference is going to be significant on the basis of the first Cochrans Q significant result. And in fact, it is 11. The Cochrans Q is 11, p equal 0.001. So the difference between 15.4 and 36.5 is statistically significant, as we'd expect. So the last one, comparing mid-semester, 25% versus 36.5%, it's the last comparison. Let's look at that one. Analyze, non-parametrics test, legacy dialogues, k-related samples, and mid-semester, end of semester, and click OK. And here we have a Cochrans Q of 6, and again a p-value less than 0.05. In fact, p equal 0.014 with 1 degree of freedom. So again, the teacher or researcher could assert that a statistically significant increase in the percentage of students who are taking the unit because they want to is observed from mid-semester to end semester. So across all of the levels, a statistically significant increase in the percentage of students who are taking the unit because they want to is observed. So that is a Cochrans Q omnibus statistic conducted first, and then a series of smaller comparisons between just two percentages are conducted with Cochrans Q again, just like a within subjects ANOVA can be conducted on the test of the difference between two means. Now a consideration is family-wise error rate, and I borrow the simulation research showing that ANOVA is robust when you use a two-step procedure with a significant ANOVA and then multiple comparisons equal to 3 as a maximum. So in the chapter devoted to ANOVA, I provide simulation evidence supporting the Fisher's LSD as an approach to protect family-wise error rate at 0.05 in the unique case of just 3 levels in your independent variable, which is the case here. If I had more than 3 levels, I'd probably have to do a Bonferroni correction or something like that here, because there aren't very many options in the test of the difference between related percentages beyond 3 levels in terms of dedicated post hoc tests.